My name is Peter Wachnick, and this is my honors capstone, which is passive audio amplification for a wildlife recording system. And a little bit of background. So the problem is that more than half of US bird species are threatened by climate change, and to track migrations and population numbers, there needs to be large-scale data collection on songbirds, both in the US and in remote regions of the world. And documenting this activity is a challenge with high costs for data collection and storage. Backyard Brains, in conjunction with MDP, developed a device to collect and store audio data that is able to identify bird songs, insects, and rainfall. And as I mentioned, Backyard Brains is a sponsor of this project with MDP, and they're based in Ann Arbor, and they're a citizen science company. So they bring science to the consumer. And some project goals for this specific project are to study bird species affected by climate change, to develop a device that is able to record bird songs, and to have this device be an inexpensive product for consumers, but have the performance that is acceptable for researchers in the field. And the origin of my RISE project came about because we discovered audio recording issues during the winter 2021 semester, in that the enclosure we had selected significantly damped audio recordings. And once we had identified this, we decided that the benefits of this enclosure outweighed the costs of the audio recordings being damped. So we brainstormed and generated a need for inexpensive audio amplification, and decided that a new microphone was too expensive, but we landed on passive audio amplification as a plausible alternative. And so that came to my RISE project, where my goals are to research passive audio amplification, generate multiple concepts, rapidly prototype these concepts for evaluation and data collection, develop a testing plan for these prototypes, and then evaluate the concepts using the testing results, and finally to produce an amplifier design and then finalize a recommendation to Backyard Brains for their device. And to give a sense of the scope of this project, here's an interface control document that demonstrates the device in its entirety, but in the red box is where I am focused. And so it's in the interaction between the ambient environment, the acoustic membrane, and then the microphone that is doing the recordings. And throughout this project, I followed a design process that was inspired by my experience in ME499 and ME450. And so I started with research, which led to concept generation, and then concept selection, prototyping, testing, and a final recommendation. And you'll see some of these arrows that are iterative. So I did multiple rounds of testing, multiple prototypes, and then multiple filters and concept selection rounds. And additionally, the purple arrows are where I would go back to if I had more time. So I have my final recommendation, but if I had more time, I would go back and kind of start all over again, and do an iterative design process to diverge again and see if there are other concepts that may work better. And the first stage that I did this semester was the research. And through passive amplification research, I found parabolic microphones, a diagram of which is seen in the top right. And so these are mainly used when sounds are too weak for normal microphones. A highly directional microphone is needed, or to boost sounds for the human ear. And this is especially beneficial in wildlife recording. So bird calls can be significantly amplified, and a bird will appear numerous times closer when recorded with a parabolic microphone, but they have some drawbacks as they're very directional, and the field recording is not capable of full fidelity recordings at low frequencies. So at a 20 hertz parabolic microphone needs to be 17 meters across, which is not feasible. I took this research and generated concepts from that. And I generated these 9 concepts, which are really rough sketches and early in the design process. And then I took these concepts, started to flesh them out. And once I had done that, I performed concept selection, where I used 4 criteria: research functionality, complexity, creativity, and design preferences of both myself and Backyard Brains to select concepts to move to testing. And these each had a weight of 0.5, which was not important to success, to 3, which was critical for success. And they were scored from 0 to 3, with 0 being no potential and 3 being large potential. And the selected amplifier concepts from this analysis were a parabolic mic with a reflector, a round funnel, and then a dog ear. And these are the names I gave them, and the sketches that these concepts are based off of. And this led me to prototyping then. And so I started CADing up these designs. And then when I was CADing, I also realized that a competitor's device had a similar passive audio amplifier. And so I added that into my concepts as well. So you can see that there on the device highlighted in yellow. And just as a note, each CAD model is about 20 millimeters in height, so they're not very large. And I began manufacturing these prototypes with PLA, but there were concerns that the layers of PLA would affect the amplification capabilities of each concept. And so I worked with Kayla at CSED to determine improved prototyping materials and learned that harder materials are better, and that SLA resin printing at the Duderstadt would actually be a great option because there's no layers, it's cost effective at the Duderstadt, and then it's easy to manufacture because I can just submit my CAD and the Duderstadt is able to print it. So once I had my prototypes, I was able to do testing. And I had 8 testing scenarios, one with each amplifier, and then one with the microphone without a case, and one with the microphone and board inside of a case. And then with these 8 scenarios, I did 1 round of testing with bird calls, where I played 4 different bird call audio files and measured the peak amplitude of each testing scenario, and then the percent difference of each amplifier from the case. And then a second round of testing where I did speaker sweep testing and played a 20 hertz to 20 kilohertz audio sweep from a computer and plotted the frequency response of each testing scenario. And this setup was in a Duderstadt multimedia room, which can be seen in the images to the left. And measurements were taken to ensure that the variables, as many variables as possible, were kept constant over the course of testing. And then an amplifier on the device during testing is shown to the right. And so the first round of testing was the bird call testing. And so I took the peak amplitude of each bird call and then from the recording. And then with the amplifiers, I measured the maximum positive percent change between the case with no amplifier and then each respective amplifier. And so from this, I found that there's a significant damping effect on the enclosure with bird calls, which can be seen in the top table. And then the amplifiers are performing as intended because they're all providing a positive percent change from the case. So they're actually amplifying the sound, which was great. But however, this testing was inconclusive for selection because, as you can see, there are 4 different amplifiers that were able to achieve the maximum positive percent change with each bird call. So this was inconclusive, and so I moved to a computer speaker frequency sweep testing. And so with this, I played a 20 hertz to 20 kilohertz audio sweep and then plotted the frequency response. And so these are 2 graphs of what the frequency response looks like. On the left is an amplifier that passed, and you can see in the red where it is amplifying the sound above that blue line, which is the case without an amplifier. And so the one on the left passed because the areas highlighted in purple were really amplifying the sound, whereas the one on the right failed, as it really follows the case frequency response closely and has very little amplification capabilities. And so from this, I found that most amplifiers were performing as intended, and these results were able to be used for concept filtering. And I needed further ultrasonic testing because the computer was not able to produce frequencies as high as necessary. And so the filtering results led me to the parabolic amplifier, the funnel amplifier, and then the dog ear amplifier in a horizontal orientation. And then my third round of testing was with a function generator because I was able to produce a 10 hertz to 40 kilohertz audio sweep in the ultrasonic range. And so for this, in these 3 amplifiers I had selected, I plotted the change in decibels from the amplifier to the no case scenario versus the frequency and compared them to each other. And you can see at the right that the green line, the frequency response of the funnel, is usually on top. And so it has the highest positive change in decibels from the no case scenario. And so looking at this data, I had my recommendation to Backyard Brains, where the use of the funnel amplifier in the field was recommended at this point. And you can see at the right, the image of the device in the field. And for the next steps of this project, an iteration of the concept generation phase with additional parabolic shapes and the location of different foci would change the amplification properties, as well as controlled testing iteration with new concepts, and then field testing with different amplifiers. So if I had time, I would like to do those three kind of main tasks, and I will recommend that Backyard Brains takes those tasks and runs with them. And so this was my project, and I'd like to thank RISE, my mentor, Professor Shanna Daly, and the PhD candidate I work with, Robert Loweth, my MDP mentor and team, and then Backyard Brains. And to answer a few of the questions for honors, I think, so how did I get involved in this project? It was really through MDP and through RISE that I was involved, and it was really kind of convenient that this issue showed up in MDP, although it was an issue for our team, but I was able to use this as my honors capstone project. And did I accomplish what I hoped to do? Yeah, I really think that this was really successful for me to learn about the design process and testing, and then also provide Backyard Brains with a amplifier that actually helps the audio recording quality of their device. And finally, how did I get connected with my capstone advisor? I had Professor Daly in her ME 499 class, which was front end design, and it was really a kind of a career changing experience for me. I really loved it. It was a very, very impactful class. And so I talked to her and asked her if she would be able to mentor me. And then I identified this gap in the recording quality of the device with her and my MDP mentor, Lynn. So that was my honors capstone and my RISE project. Put any questions you have in the comments. Thank you.